Hi, I'm Professor Goings. In this video, I'm going to look at the concept and some computations for the curvature of a space curve. All right, so if I look at these two space curves here, we can see that they both curve. In other words, they're not straight. They've got some sort of an arc to them. But this one seems to be curving more. So what we want to do is we want to figure out how can we computationally represent, or how can we quantify curvature, because this one should have a larger curvature than this one. So how can we work with that? Well, what I'm going to do is I'm going to attach some unit tangent vectors along these curves, and let's see what we notice. So again, each of these blue curves are going to be unit tangent vectors. And for simplicity, let's say we both did that over the same arc length, right? So maybe this, from this point here to this point here, maybe that has arc length 1, and same thing from here to here that would have arc length 1. So you can notice that the unit tangent vectors in this first case, they don't really change a whole lot. They do change, but we'll go from here to here to here, so they do change, but the change is subtle. When I have a curve that curves more, so let's say this, when I have a graph that curves more, the unit tangent vectors change more drastically. So that gives me an indication that one way to quantify curvature is to look at the rate of change of the unit tangent vector. So let's take a look at, well, let's say this. Let's say over that interval, let's say this is a change in length s. Same thing here. Let's say that's also a change in length s. And like I said, for simplicity's sake, let's just say we did it over the same amount of arc length. So those are all over the same length of the curve. So in this case here, the unit tangent vectors don't change much. Over here, the unit tangent vectors change more drastically. So conceptually, curvature is somehow related to the rate of change of the unit tangent vector. Okay, so let's see how that's going to work in this case. So once again, let's draw a curve. Let's pick some unit tangent vectors. And let's say each one of these has same arc length. So I'll say change in S for the arc length. Okay. So again, the curvature is equal to So again, it's the rate of change of the unit tangent vector. So let me start by saying it's going to be a derivative of the unit tangent vector. And so what is the variable that what's the differential in this case? Well, if I keep making these delta s's smaller and smaller, that's going to end up being a differential with respect to arc length. And we really don't want curvature to be negative, so what we do is we say that curvature is going to be the magnitude of that, okay? So curvature is the magnitude of the derivative of the unit tangent vector with respect to arc length. Traditionally, the notation for curvature, or the symbol used for curvature, is the Greek letter kappa. Okay, so the Greek letter kappa is equal to this right here. Now, here's the advantage of this for curvature. It's more intuitive. It's how does the unit tangent vector change per unit of arc length? The problem with that is it's less computational. So it's what we have to do in order to compute curvature is I have to convert this this derivative into arc length, and not arc length, and into the parameter for the graph, which would be lowercase t. So I have to convert this to the parameter t. These videos can only be so long, and I'm sure people out there only want to see so much detail, so I'm not going to prove this. However, if you want to see me prove it, if you want to see the details going from this to the following formula, let me know in the comments below, and I'll be more than happy to create another video showing you how I get the following result. But the result that we are going to use is the following. The curvature, okay, is given by the reciprocal of v, which is the dr dt, which is the derivative of the parameterization, multiplied by the derivative of the unit tangent vector. So this one is more intuitive, this one is more computational. But notice that even the intuitive or the more computational representation of curvature does have a rate of change of the unit tangent vector. So it is, you could say it's proportional to the rate of change of the unit tangent vector, which again provides a very geometric idea. All right, let's do a couple of examples of computing curvature. So let's see, where are we on the video? Right, our screen right here. Okay, so for example, find the curvature. Okay. Part A, let's look at r of t is the vector function, or the space curve, t plus 1 for t minus 3. For part B, let's look at the space curve, r of t is equal to, let's do a cosine t, a sine t, where we are going to assume that a is a positive constant. Okay. So compute the curvature for both of those space curves. So solution for part A. So again, what we have to do is use this formula down here, which means I need to find a couple of things. I need to find the vector v, which again is the derivative of r. Then I have to find the magnitude of that. I have to find the unit tangent vector, the derivative of that, the magnitude of that, and then put those all together. So let's see how that works. The vector v, again, is the derivative of the space curve, which in this case would be the derivative of each component would be 1, 4, 1. Okay, the magnitude of that would be the square root of the sum of the components squared. So that's 1 squared plus 4 squared plus 1 squared, which would give you 16, 17, 18. So that's the square root of 18. 18 is not a perfect square, but 18 is 9 times 2. So that brings out a 3. So I've got 3 root 2. So the magnitude of the velocity vector, again, interpreting that as velocity, would be 3 root 2, or in other words, just the magnitude of the derivative would be 3 root 2. All right, the unit tangent vector, remember, is the vector v over the magnitude of v. So in other words, we normalize the vector v. That would give me, take this vector and divide by this constant, or that scalar. Scalar multiple of a vector means I can distribute it through. So that would be the vector 1 over 3 root 2, 4 over 3 root 2, and then 1 over 3 root 2. So that right there would be the unit tangent vector for this vector function, or that space curve. All right, next thing I need is the derivative of that unit tangent vector. And notice that each one of these is a constant. So the derivative of that is the 0 vector. The derivative is the 0 vector. The magnitude of the 0 vector is 0. Any scalar times 0 is 0. So therefore we find that the curvature in this particular case is 0. Does that make sense? Well, let's see. This space curve, what does it look like? Well, if you watch the video that I made on lines in space, the graph of this is a line in space. So in other words, I need a longer marker, so I'll put 2 of them together. So I have this line. A line doesn't curve. Line has no curvature. So we say that it has curvature 0. So that matches up to our intuition with that. Conversely, if you know that the curvature is 0, the only space curve that happens for would be a line. So it's actually an if and only if statement. Have a line, curvature is 0. Curvature is 0, then you have a line. All right. Let's look at part B. Solution for part B. So for the space curve, a cosine t, a sine t, start with the vector v, which would be negative a sine t, a cosine t. So negative a sine t, a cosine t, differentiating each component. The magnitude of v would be the square root of, so I've got negative a sine t squared plus a cosine t squared. So I square both of those, I get a squared sine squared, a squared cosine squared under the square root. Factor a squared out. Sine squared plus cosine squared. So what trig identity is that? Okay, Pythagorean identity. Sine squared plus cosine squared is 1. So this is the square root of a squared. Remember that we said a was strictly positive, so therefore this is equal to a. So the magnitude of the vector v is a. Then for the unit tangent vector, v divided by the magnitude of v, so that's v over the magnitude of v. So that means I'm taking this vector here, which is v, dividing it by a, so that would be negative a sine t, a cosine t, divided by the scalar a. So I can divide each component by a, leaving me with negative sine t and then cosine t. So this would be the unit tangent vector. All right, then I need the derivative of the unit tangent vector. So that would be negative cosine t, negative sine t. The magnitude of the unit tangent vector, or the magnitude of the derivative of the unit tangent vector. For the same thing that we got over here, it'd be negative cosine squared, so cosine squared plus sine squared, the square root would give you 1. Finally, putting this together, I get the curvature for this space curve is the reciprocal of the magnitude of v, so 1 over a, times the magnitude of the derivative of the unit tangent vector, which is 1. So we come up with the curvature is the reciprocal of a. Okay, so let's talk about that, what that means for a moment. All right, look back at the original space curve. Does that make sense, or where does that come from? Well, a cosine t, a sine t, if a is positive, then the graph of this is going to be a circle centered on the origin of radius a. So let's look at a couple different sketches for that. All right, so one possibility would be if a is, say, 1. Let's say this is a is equal to 1, and over here, let's say this is a is equal to 2. So what this says for the curvature is that the curvature is the reciprocal of a, so it's the reciprocal of the radius. For this graph here, for that circle, we're saying that the curvature is 1. For this one, we're saying that the curvature is 1/2. So the smaller the circle, the larger the curvature. The larger the circle, the smaller the curvature. So again, curvature and radius, or curvature and size of the circle, again, using the radius, have a reciprocal relationship there. This is also an inequivalence where if I have a space curve that has a constant, a positive constant curvature, then it's a circle. Okay, so if I have a circle, the curvature is a constant. If I have a constant curvature, then the space curve is a circle.